Welcome to Ready to Derive. In this video, we'll be learning to approximate the area under a curve. Now, why might we want to do that? Well, in my last video on area and accumulation, which I'll link in the notes below, we learned that, take this example. Say you are traveling 60 miles an hour on the highway on cruise control for 30 minutes. We learned that the area under that velocity curve or rate curve would give us the distance traveled. So 60 times 30 minutes is half an hour, 60 times a half, that means we've traveled 30 miles. Well, what if your rate curve looked like this? So I know it's a straight line, but we refer to it as a rate curve. So you're starting at 60 miles an hour and you steadily decrease until your speed is 0. Well, again, to find the distance traveled, we find the area under that of that triangle, which is just half the area of the rectangle in the previous example. So your distance that you traveled is 15 miles. But what if your rate curve or velocity curve looks like this? Well, finding that area, well, we don't have a geometric formula for that. Might look like a quarter of a circle, but it's not. So we need to find a way to work out that distance, and that is what this video is all about. We are going to be using rectangles and trapezoids, so geometric objects, to estimate the area under that curve. So without further ado, let's begin. Okay, so let's begin our investigations with a scenario. Suppose the odometer on your car is broken and you want to figure out the distance you have traveled over a 30-minute time interval. You have your passenger take a speedometer reading every 6 minutes. So let's pretend you're on the highway, so you're not stopping at traffic lights or anything like that. Let's say, and here's the results that your passenger recorded. And the question that we would like to answer is to find approximately how far the car traveled over the 30-minute interval. Now, I chose every 6 minutes because 6 minutes, when you convert that to hours, it's 6/60ths or 1/10, which is 0.1. That makes the decimals very nice. And to find out how far we traveled over 30-minute interval, let's sort of break it down over, say, the first 6 minutes from 0 to 0.1. Now, you have to to find distance traveled, you have to take your speed times time, but we don't know whether to use 60 or 58, but so why not compromise and use the average of those two, which is 59, times 0.1, so you did that for 0.1 of an hour. That works out to you've covered 5.9 miles in that interval. And let's just repeat. So the average here would be 54. So that comes out to 5.4. The average here is 44. And that comes out to 4.4 miles. Since we're slowing down, we're obviously covering less ground every 6 minutes. 5.1 equals, that will equal 3. And the average of 22 and 0 is 11 times 0.1, which is 1.1. And if we add those all up, we find that we have traveled a distance of 19.8 miles. Well, approximate distance. We don't know the exact distance because we had to pick a speed for each interval, and we chose the average speed. But it's pretty accurate. Maybe we went around 20 miles. It's pretty close. So the question we might ask is, what does this calculation have to do with area under a curve, which is what this video is all about? And we'll find that out in the next slide. So here is the recording of our speedometer readings, and here's a plot of those values. And we don't know exactly what our velocity was. We can't draw an accurate plot of a velocity over the whole time interval, but we could sort of imagine maybe it looks like this. And I know, here, for example, in this little region here, we sped up and then slowed down. And then otherwise it was a general slowing down, pretty consistent slowing down over that interval. So let's review the first calculation we did to approximate the distance we traveled over the first 6 minutes. Remember, we averaged 60 and 58 to get 59. I'm just going to write that out as half 60 plus 58. Then we multiplied that by 0.1. Now, that's interesting because it may look familiar to you, but that is in fact the area of a trapezoid, the formula for area of a trapezoid, where this is, so that's like B1, B2, and this is H. Now, what does a trapezoid, let's have a look at this. What is a trapezoid is defined as a quadrilateral that has two parallel sides, sometimes called the bases. So this is B1 and B2. They don't look like bases. If this trapezoid was turned on its side, then you would see why they're called the bases. And H is often referred to as the height of the trapezoid, but it's really the distance between the parallel bases. So where is this trapezoid? This calculation, what does it give us the area of? Well, let's look up here. Here's a trapezoid right here. So what are the bases of this trapezoid? This is 60. This one is 58. The distance between the bases is 0.1. And the area of that trapezoid would be given by that green calculation, which is an approximation to the distance traveled, or the area under the curve. Now we do miss this little portion here, but that's the breaks when you're dealing with approximations. We'll never be sure how precise it is. Let's just do one more calculation for demonstration purposes. So 58 plus 50, that's how we average them, and then we multiply those by 0.1. And where is that trapezoid? Well, this trapezoid looks like it's a lot more accurate. So 58 is shared, that side there. This base has length of 50 here. The distance between the bases is 0.1. So the area of that trapezoid is actually closely approximates the area under the curve, assuming that the blue curve is correct. And so that is a very good estimate of the distance traveled over those 6 minutes. This whole method is using trapezoids, is referred to as a trapezoidal approximation. And we can imagine that if you actually recorded the velocity maybe every minute, you'd have an even more precise estimate of the area under the curve, which, remember, is equivalent to the distance traveled over that interval. So now we're going to approach the same problem, but this time using rectangles instead of trapezoids. Because rectangles, the formula for the area of a rectangle is base times height, it's much simpler than that for a trapezoid. So you'll see the benefits. So first of all, we have to think about, well, the base of each rectangle is still going to be 0.1 as it was for the trapezoid. So let's kind of think about what the rectangle might look like. So the base of the first rectangle will be 0.1. But the question is what to make the height. Should the height be 60 or 58 or somewhere in between? Well, now we have to be specific about what type of rectangles we're using. So we can look at what are called left endpoint rectangles, where the upper left endpoint of the rectangle needs to lie on the curve. So left endpoint rectangle would look like this. So we can work out the area under of this rectangle, and that will help us to begin finding the approximate distance traveled. So the area would be 60 times 0.1. And then, so 60, we use that 60 times 0.1. And then let's look at the next rectangle. So what is the height, upper left-hand endpoint? What is the height of that rectangle? It's the 58. So the area of this would be 58 times 0.1. And let's proceed. What would be the area of this? Upper left endpoint is 50. So 50 times 0.1. Continuing on, we have 38 times 0.1. And finally, the very last rectangle. Notice we don't actually use the 0. We would just have the 22 times 0.1. And if you work that out, that comes out to 22.8 miles. All right, so if we do left endpoint rectangles, another choice could be right endpoint rectangles. So the right endpoint rectangle, as you can probably imagine, the height of the first rectangle is going to be where the right endpoint falls on the curve. So the area of that first rectangle would instead be 58 times 0.1. So notice we don't use the 60, but we use the 58 plus 50 times 0.1, right? So that one there, that would be the next one, 50 times 0.1. And just to save us a little calculation, here's the other ones. All right, so I'm going to put plus ... You can fill those in. So we're going to use the 38, we're going to use the 22, and this time we do have a rectangle. It's really hard to see, but the very last rectangle actually has a height of 0, right? Because all the upper right endpoints have to lie on the curve. So we are going to use that 0. So our very last calculation will be 0 times 0.1, and that works out to be 16.8 miles. So in the next slide, we'll compare the rectangular approximations with the trapezoidal, because there's a very interesting connection. So let's make some connections. So when we use the left endpoint rectangles, and I'm going to take the second rectangle as a sample one, we got an approximation, and I have new notation to introduce to you. You see the L5, L stands for left endpoint rectangles, and 5 means there were 5 of them in our approximation. And we can see that we kind of, the left endpoint rectangles seem to overestimate the area under the curve, because you know, for example, it kept that purple region means the region by which it's overestimated on that interval. So there was a general feel that that must have been an overestimate. When we used right endpoint rectangles, let's do a sample one here. Now we see that, oh gosh, it seems like we are definitely underestimating the area, and that's because the curve is actually decreasing, so that won't always be the case, but in this case it was. And the notation is R5, and we got 16.8 miles. Again, it felt like an underestimate. So what about the trapezoids? So when we use the trapezoids, well, we were using both these points, and this area here, it seemed like actually the best approximation, right? There's no, basically, we're not entirely sure because we don't know what the blue curve, velocity curve does in between those points, but it looks like the best approximation. And we got 19.8, somewhere in between. Where in between? Well, actually, exactly halfway. If we take 22.8, the left-hand approximation, and the right-hand approximation, add them together, 22.8 plus 16.8, and if we divide by 2, we get the trapezoidal approximation, which is pretty interesting. Let's take a little look and see why that is. If we remember the area of a trapezoid, the formula was this. And so that's B1, that's B2, H. If we just keep the half out there and distribute the H, we get this. B1H plus B2H. Well, what is B1H? Well, that is just the area of a rectangle whose height is B1 and whose base is H. And what is B2H? Well, that is the height, that's the area of a rectangle whose height is B2 and whose base is H. So obviously, and then you put this half in front, so you sum up those two, and then you take half of it, so you basically get the average. So here's a very useful, important fact, is that the trapezoidal approximation will be the average of the left and right rectangle approximations. So to practice the different concepts, different methods of approximation we've learned, we're going to do a modified AP Calc question from the 2022 exam. So an ice sculpture melts in such a way that it maintains its conical shape as its base radius r decreases in size. And this is a table of selected values of r prime t, the rate of change of the radius over a period of 12 days. And the first thing you need to observe is that not all the intervals are the same length this time. So keep that in mind as we do our calculations. Notice that there are 4 intervals, so we're going to approximate this in different ways. So let's practice everything we've learned. So we are going to approximate the total change in radius of the ice sculpture over the 12 days. And we understand that to mean approximating the area under the curve if we were to graph r prime, which we're not actually going to do now. We're going to try and sort of not have to rely on the graph and work these things out algebraically. So let's start with left rectangles, and we have 4, right? 4 intervals. And when we're doing left rectangles, remember that we start with the height of the very first rectangle will be the leftmost value. So that will be negative 6.1, but that negative 6.1 spans an interval of 3. So from 0 to 3, we assume that the rate of changes stays constant, negative 6.1. And then for the next one, so we did, and I have a nice way of coding this. Notice that it's like a little Tetris shape. I have negative 6.1 times that interval 3, and the next interval, the next value will be negative 5 times this interval. So let's see if you can see that, negative 5 times this. So minus 5, and that interval has a length of 4. So I'm kind of maintaining looking at these shapes. So then we're going to do, so we use minus 5. Now we're going to use minus 4.4. I won't keep messing up the diagram because it'd be hard to read. And then we're going to use negative 3.8 for the interval of 2. Notice that we are not using the negative 3.5 because these are left endpoint intervals. And this comes out to be negative 59.1 centimeters. So we estimate that's how much the radius decreased over the 12 days. And now let's look at it with the right value. So let me get this away here. And when we're using the right ones, notice, remember, we don't use the first value, but we are going to use the negative 5. But that's going to apply to the 3, that interval of 3. So now I'm kind of creating little, almost like Tetris pieces that look oriented that way. And then we're going to use negative 4.4 times 4. And let's see, negative 3.8 times 3, and then negative 3.5 times 2. And that comes out to, our estimate there is negative 51 centimeters. And now we know for our shortcut that for the trapezoidal value, I'm not even going to work out the trapezoids. I'm just going to average these two values. And that comes out to negative 55.05 centimeters, and that again is maybe a better estimate of the decrease, the total decrease in the radius over the period of 12 days. So for our last exploration, we're going to learn to approximate the area under a function rather than from a table of values. So we are going to approximate the area under the function x squared plus 1 and between x equals negative 1 and 2, and we're going to use 3 rectangles. Just, we know that's not a very accurate representation, but it kind of is easier calculation wise. It just saves time. The first thing we need to realize is that that distance is from negative 1 to 2 is 3, and we need to divide that into 3 rectangles of equal width, so we would get 1 there. And what I like to do for this, because now we don't have a table of values, but we can construct a table of values. We know that our lowest x value is negative 1 and that the intervals have to go up by 1. And then we just have to, if we find f at those values, then we kind of have it ready to go. So f of negative 1 would be negative 1 squared. 1 plus 1 is 2. I won't do this for everyone, but just to demonstrate a couple, if that was 0, that would come out to 1. And then you can, continue that. This would be 2, and this would be 5. 2 squared plus 1 is 5. So if we want to do, let's start with the left endpoint rectangle. So again, you could have read this off the graph, because when x is negative 1, the height of that rectangle, f of negative 1, we can read it as 2. But if the graph didn't pass through very nice points, you wouldn't be able to read it off. You have to use the function. So that would be 2 times that interval, which is 1. And so we use the 2. Remember, we use that value. So 1 times its interval, 1. And then we use this, 2 times 1. And we don't use the last value. And this comes out to be 5. And then we repeat. For the right hand one, so the first value, let's just do that very first rectangle. The height of the first one is obviously f of 0. So we don't use this, we use this. So it's 1 times 1. We use that value, 2 times 1, and we use that, 5 times 1, and that comes out to be 8. And we know that we could figure out the trapezoidal approximation, but instead we're going to introduce you to a new type of rectangle used to approximate areas under curves. So we'll conclude with the midpoint rectangle. So what does that look like? Well, first of all, we need to know how many. We're going to use 3 again. So the first rectangle will still go from -1 to 0, but the height of that rectangle will be determined by the midpoint of that interval. So let's see, here we go, like this. So what will the height of that be? Well, it's just going to be f of -0.5, and the width is going to be 1 again. So let's make that rectangle there. So this, a little off, but okay. And then we can see that though, even though we missed this area here, we kind of made up for it right here. Not perfectly, but it's a, pretty decent approximation. So where will the next rectangle, the midpoint of the next rectangle, it will be here at 0.5. So let's do that there. So what will its height be? Well, actually, it's technically f of 0.5, but it looks like it will be equal to f of -0.5 based on the symmetry. And then the next one will be at 1.5. So let's build off that rectangle. So this height here will be f of 1.5. And the width of each rectangle is 1. I'm just going to move to use white now because the red is so loud. So what is f of -0.5? Well, we have the formula. It's -0.5 squared plus 1. What is f of 0.5? Well, 0.5 squared plus 1. I'm not even going to write the times ones because that's sort of obvious. Okay, and then this will be f of 1.5 will be 1.5 squared plus 1. And this comes out to be 1.25. The first rectangle, and the second rectangle is also 1.25. And the last one is 3.25, and we get an approximate area of 1.75, which seems like an improvement on the left and right endpoint rectangles. But previewing what's coming in the next video is like, how could we find the area under curve, say between a and b under f of x, more accurately? Well, by increasing the number of rectangles. And if we increase the number of rectangles, they get narrower and narrower. So check out this. And you could use left endpoint rectangles, right, midpoint. In fact, any point in the midst of that rectangle will suffice. There's going to be some, differences in accuracy, but you can imagine if we got to infinitely many rectangles that are each infinitely thin, then we might actually be able to accurately work out the area under a curve. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.